Hello, everyone, and welcome to We Meet at Digital Days. My name is Lisa Richter, and I will moderate this presentation. We are very pleased that you took the time to participate in our conference. The topic of this presentation is hardware design in hints for sensors. Our speaker is Julian Saavedra Molano. He will hold the presentation and will answer all of your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You will receive the link to the presentation in the next few days, and the recording will be available at our website shortly. So now I will hand over to our speaker, and I wish you an exciting presentation.
So thank you very much for the introduction. I am Julián Saavedra. I am hardware engineer, and I am very glad to be part of the Digital Days 2021 and to present the hardware design in guides for sensor. As you know, nowadays there are a sensor almost in every single board. To get the best of the sensor, we need to take some consideration from the beginning of the design. So let's see what we are going to see. So first, we are going to define what MEMS sensors are and silicon-based sensors. Then, so just to make sure that we are in the same page, then we will see how to integrate sensor in the PCB. We'll start with the footprint, then designs rules, layout hints, and then once we have our layout finished, we can see what the soldering guidelines are. Then at the end, we will see how to avoid some miss issues on how to get the best of our sensor. For example, with the temperature sensor, you can sense either ambient temperature or you can also sense the temperature produced by a heating element, for example. And finally, we will see how to avoid mechanical misuse. So first, MEMS sensors. So MEMS stand for micro electromechanical system. And what we do with this membrane is to transduce any physical quantity from into electrical signals. And once we have the electrical signals by means of this ASIC, which stand for application specific integrated circuit, we can do signal conditioning, processing, and calibration. Then we can get the signals in either digital or analog domain. On the other hand, we have silicon-based sensors. Here we don't do any kind of transduction. Here we know that in the BJT transistor, for example, there is a correlation in the PN diode, a correlation between voltage and temperature. So we use this correlation and we have again by means of a ASIC, we can do signal conditioning, processing, calibration, and get again the signals either in the digital or analog domain. So let's start footprint, the first step. So here you can see the footprint, for example, for the accelerometer sensor, the ITDs. This, please, we do recommend the most important thing is to have non-solder mask defined for the lamp pattern. Then you can see on the right side the tables. These tables, as for example, we have a LGA pad spacing for about 0.1 millimeter bigger than the pin, and the same case for the opening for the solder mask, 0.1 millimeter. So don't worry, this information you will find in every manual for every single sensor that we have available, you just go on into the website. So we finish the footprint, we can just go to the placement. Here, the important concept is to have this keep out area. And what is it? Just to keep 2 millimeter distance from the edge of the sensor. And in this area, please, as you can see in the examples, please do not place any kind of screw holes or mounting holes or vias, or even avoid using routing underneath the sensor. You can see how to do it properly on the bottom side. Then we have finished our placement in the layout. We can start with the layout itself. The first to have into account is to have, when doing the fan out, when doing the tracing coming out of the footprint, please make it at as symmetry and balance as possible. The symmetry will help the sensor by soldering with self-align, as you can see here. Then please, once you have done the fan out of the sensor, we recommend, if you have the possibility to have two from a multi-layer PCB, to place in the second layer, you can place the ground plane. And if you have, for example, analog and digital grounds, please keep it separated as possible. Here we will, as we already discussed at the beginning, we can have digital interfaces. For example, here you can see the SPI interface, but we also can have I2C interfaces. With SPI, we can get up to 10 megahertz speed, and with I2C, you can get up to 1 megahertz. There is already kind of fast interfaces, which with the high speed will pose a challenge, because there will be straight capacitance. These straight capacitance, as you can see on the example, they will influence the quality of the signal. So in order to get a good quality, as you can see on the bottom side, you can either reduce the pull-up resistor, or you can make the trace as short as possible. But keep in mind, by reducing the pull-up resistor, you will consume more current. So this is a very special case. What you see here, this for the 3-pin SPI humidity sensor. And of course, you have also the possibility to place ground underneath the traces. So we have finished our layout. We have a good layout. Then what we want to do next is to do the pick and place and the soldering process. For soldering, thickness and soldering paste pattern are very important. So please use a stencil thickness from 90 to 150 micrometers. Then, of course, using a stainless steel stencils, very advisable, and with the opening pad for the stencil of about 70% to 90%. And trapezoidal and rounded corners aperture walls are very recommendable here. And as you can see, the sensors are very small, so the alignment is very important when doing the placement, to get a good connection between the footprint and the sensor itself. And you see here, this is our temperature sensor. You can see there is a big exposed pad. So for this kind of pattern, we recommend to have no more than 20% in every pad, no more than for every, I am talking about the solder paste, no more than 20% of the overall solder paste applied to one device. This is very important to keep it in mind. So then we can place our sensor here. We do recommend to use pick and place, but as you see in this sensor, there is a white area. This white area is actually the silicon membrane. Please avoid touching it, avoid picking the sensor in this area, because if you do so, you can add an offset in the measurement, or even worse, you can damage the sensor. So please avoid do that, and no handling solder process. There is not recommendable, because you might add some mechanical stress, which is not desirable. Of course, use no clean solder paste, and usually in the for soldering in the reflow soldering, you can see that it is recommended to have a rep down less than 6 degrees per second. But for our sensor, for the sensor in general, it is recommendable to use than 3 degrees per second. And mechanically speaking, you please avoid high amplitude resonant vibration. So all these issues that we already discussed, you can go more in detail and just click here. You will find here our application note for MEMS sensor PCB design and soldering guideline. Just click there and you will find more information about it. So we already talked about mechanical stress. So how it looks like. So mechanical stress, here we have an example. There is one way, for example, let's say we place one via underneath the sensor. So when soldering, when the solder paste reach the liquidus temperature, the sensor will sink. And by sinking, they will touch then this via, and the via will be like a hump. Then when the solder paste goes back to the solid state, then there will be forces. The junction between the pad and the pin of the sensor will create forces which, as you can see with the errors, the amplitude and the direction are kind of pushing the sensor, but the via will be pull the sensor. So sorry, the other way around. So this will create stress in a mechanical stress, which is not desirable, and you will need to avoid. And the other option is when you don't apply the same quantity of solder paste. So if you apply, for example, you can see here on the left side, you have more solder paste than the right side. So this again, there will be different magnitudes and then forces which are pushing and pulling, and they will create an imbalance. So this imbalance, we will also then end up in mechanical stress. So now let's go to the next chapter, avoid misuse. Let's say we have the temperature sensor. As I already said, temperature, you can measure either, for example, ambient temperature, or you can measure the temperature be in the PCB or on the component. So for the first example, let's move on with ambient temperature. Here, let's say we have our heat source IC and our sensor. As you can see there, you want to keep it as isolated as possible, and you want to keep it as far as possible from each other. And the ground connection, just make it in one place, just through one trace, and as far as the ground plane as possible. So if you want to improve the measurement and get a better isolation, you can add a cutout area, or even better, add some perforation. It will just improve the thermal isolation. This temperature sensor, as you can see there is a spouse pad. This spouse pad you can connect through a via to the bottom side of the PCB. There you can get the surrounding temperature, and then will get a more accurate measure of the ambient temperature. Then here you can see a real layout example of how you can implement this temperature sensor for measuring the ambient temperature. So let's move to the other way to measure temperature. Now we want to measure the temperature produced by a component. So you can see here the spouse pad is directly connected to the die of the sensor, and this will just help to have a better thermal conductivity. So we can use this in order to get the temperature of a heat source. By heat source, we find, for example, MOSFET or microcontroller. They also have a spouse pad which are connected either to ground or are connected to the voltage supply to VCC, for example. So connect these two as close as possible, and you can use, for example, an inner layer to connect both exposed pads. Or even better, if you can use the bottom side of your PCB, you can just reduce the distance and place the sensor on the bottom side. Here, once again, one example of how you can implement this example. So we have an example here. We took the first option of measuring ambient temperature. We took the pad open to, first you can see in red, the pad open to the air, and the pad just leave it alone, just without any kind of connection. As you can see here, if you left the pad open to air, the response is much faster. On how much? 7 seconds faster. So let's move on. Now, some recommendation for the storage condition for the humidity sensor. This is quite important. We recommend to have the storage temperature of about 10 degrees to 40 degrees with a range of 20% of relative humidity to 60% of relative humidity. So in order to get a better measurement, you can add also when you are using a humidity sensor, you can add some cutout like this. So you can allow that the air flow from one side of the PCB to the other. And if you cannot keep the condition that we already taught, then you can do you need to do recalibration. So, but the sensor they are able to do auto recalibration, but we recommend to do recondition process. First, just baking 10 degrees to 100 degrees to 110 degrees at 5% relative humidity for 12 hours. Then second step is to do rehydration, 20 degrees to 30 degrees at 75% relative humidity for 12 hours. Then you will be sure that the recalibration is done and you will save some time. So now we can go for the last section, is how to avoid mechanical issue. So first, you can see here we already talked about the silicon membrane. Please leave it alone, don't touch it. Once again, it will add some kind of offset or even worse, damage the sensor. And another example is please do not use any kind of molding, because by molding, as you can see here, the membrane, they are had also, they have some holes which allow the air flowing into the sensor and to make the measurement. So if you use molding, you will obstruct these holes or block these holes, which then you are not able to have any kind of measurement there. So please avoid doing that. So finally, what we see today, a summary. So in order to obtain the best performance of a sensor, best practices in the design phase need to be considered. For instance, proper footprint design, no routing and no mechanical holes underneath the sensor, ground separation, and short traces. As we see already with digital interface, they might be very tricky. They might pose a challenge. Good signal quality can be obtained by reducing the length of the traces and decreasing the pull-up resistor. When measuring also ambient temperature, it is recommended to connect the exposed pad to the bottom side of the PCB by means of vias. Additionally, cut areas and or perforation are very recommendable for increased thermal isolation. And the other case, if you want to get the heat produced by a component in a PCB, the exposed pad of the sensor and the exposed pad of the target unit should be connected with minimum possible distance. And finally, again, silicon membrane on the top should not be touched or blocked. So This all sensor that we already saw here, you can just go on the link and you can have a look on our products. You will find a lot of variety of sensor and also the radio frequency modules. Please go there, have a look and enjoy. Thank you very much.
Thank you, Julian, for your great presentation. Now we will have a look at the questions. You've got now the option to set the questions via the chat function in the panel. So just have a look what's coming in. So maybe a first question. Are the footprint of Würth Elektronik sensors available on the website?
Yes, they are. Just go in the link that I already showed you. You will find our sensors. You can find there also there are footprints already done for Eagle or Altium. Or if you have another EIDA software, then you can just follow the recommendation that we have from our manuals.
Okay. And what could happen if the opening of the stencil is the same size of the land pad?
Okay, it's a good question. For example, this is very important if you have a big expose pad. So if you have a expose pad that big, then there will be a lot of solder paste. So by soldering, it can happen that the sensor lean on one side and the other side of the sensor will not be connected, or you might have some short circuits between the pads.
Okay. Another question, is vapor phase soldering allowed on sensors with openings?
No, that's a good question as well. No, actually not. We recommend here to have every flow soldering, because if you are using vapor phase soldering, they might be that these very small particles will go in this hole that holes that we already saw there, and will block the hole. So they will uh, not allow that some air when it's going through the membrane. So please use reflow soldering. It is the most recommendable process to to do it.
Okay. Another question to the humidity sensor. Can the humidity sensor also be soldered by reflow, and what precautions need to be taken?
Yes, by reflow soldering, you can also, as we say, reflow soldering is advisable in this case. What the precaution that you should take is that the wrap down. So we say that wrap down usually you find in the jaded standard it should be less than 6 degrees per second. We recommend to keep it less than 3 degrees per second.
Okay. Another question. Are there also 3D models of the sensors and thermal simulation models?
We do not have the stencils. For the stencils, if I got it right, for the stencils you can find them in our footprints what you need to keep there. So if you have a Eagle or Albion, they are already standard there, so you don't need to care about it. And the 3D model, if you are meaning about the step detail, about the 3D of the component itself, we have there. But if you are meaning about the thermal conductivity, I need to double check this, so I will then reply via email.
Okay, sounds good. Another question. Which impact does close via placement has on the pressure sensor?
So if you put it underneath, you might have this effect that we already saw, this mechanical stress, that because you are pushing the sensor on the other direction and your pad pins are pushing and are pulling the sensor to the PCB, so you will have some mechanical stress, which, as we already saw there, it should be avoided in order to avoid some offset.
Okay, great. So I think there are no questions left. If there should be more questions, you can just write us them via the email address exhibition@we-online.com. So thank you very much, and thank you all for your attention. I hope you enjoyed our presentation. And the next presentation topic is simple and secure cloud connectivity solutions for IoT applications. The presentation starts at 3, and hopefully see you there. Enjoy our digital days, and goodbye.
Bye bye. Thanks.